We can categorize QoS implementation tools into three broad categories: classification and marking tools, congestion avoidance tools, and congestion management tools. Under classification and marking tools, session traffic is classified into different priority groupings and packets are marked. Under congestion avoidance tools, traffic classes are allotted network resources. Some traffic may be selectively dropped, delayed, or remarked to avoid congestion. Weighted random early detection regulates TCP data traffic in a bandwidth-efficient manner before tail drops caused by queue overflows, basically congestion, occurs. And under congestion management tools, when traffic exceeds available network resources, or we have congestion, then traffic is queued to await the availability of those resources. Common Cisco iOS-based congestion management tools include class-based weighted fair queuing and low latency queuing, or the CBWFQ and LLQ algorithms. If we look at this diagram, you can see the three sets of tools being used in sequence. From the ingress interface on a router to the egress or exit interface of the router, you can see that traffic is first classified and then marked. Notice in the graphic how the packets before being classified are all seen here as gray. As they're classified into different classes, they're marked in the IP header, indicated here with the colorization of the different packets. Congestion avoidance is where traffic is policed and selectively dropped. This is where network resources are allotted into different priorities. Packets are put into different queues based on different weights or sizes. The main congestion avoidance tool that's used in Cisco devices is weighted random early detection, or WRED. If queue buffers fill up, packets may be dropped proactively as to avoid congestion. Lastly, we have the congestion management section where packets are put into their queues and are scheduled and shaped based on the network priorities or policies that have been applied. If we look a little closer at QoS traffic marking, we can see that traffic marking happens at both layer 2 and layer 3. At layer 2 we have class of service, or CoS, which happens using the 802.1q VLAN tagging and 802.1p quality of service protocols. Traffic marking at layer 2 happens on the local area network and is limited to the LAN using layer 2 switches. Under Wi-Fi, traffic marking happens with the Wi-Fi Traffic Identifier field, or TID. With MPLS, you have the experimental, or EXP field, also at layer 2. At layer 3, with IPv4 and IPv6, we use the TOS and traffic class fields using IP precedence, or IPP, and DSCP, the differentiated services code point. With layer 3 traffic marking, the marking can go from router to router, and therefore the QoS marking can be carried end-to-end across the network. In this slide, you can see how QoS marking happens at layer 2. We have an Ethernet frame, and the 802.1q protocol can be inserted between the source address and the type length field. You can see the two fields inserted into the Ethernet frame: the TPID field and the TCI field, or Tag Control Information field, which contains a 3-bit PRI priority field which identifies the class of service, or CoS marking. The class of service markings have 6 different values: best effort, medium priority data, high priority data, call signaling, video conferencing, and voice bearer for voice traffic. Bits 6 and 7 are reserved for network control information. At layer 3, QoS is implemented in the IPv4 and IPv6 packet headers in the type of service field and the traffic class field. In the older implementation, class of service at layer 3 was implemented using IPP and TOS. The IP precedence is 3 bits, and the type of service is 5 bits, and you can see them there in the 8 bits. The classifications have 8 levels, which map to the layer 2 class of service. You can see there routine, priority, immediate, flash, flash override, and critical. Once again, values 6 and 7 are reserved for network control information. The current implementation of QoS uses the differentiated services code point and explicit congestion notification fields, or DSCP and ECN. DSCP and ECN map directly over the 8 bits of the IPP and TOS fields, and the DSCP field is backwards compatible with the IPP field. You can see in this example that an IPP classification of 5 involves the 1 here and the 1 here. If you have IPP and you have 3 bits, then this would be a 4 and a 1, which would be a 5, which would signal a critical flow. Under the DSCP specification, you have 6 bits, 1, 2, 3, 4, 5, 6, and this is a 32, and this is an 8, and 32 plus 8 is 40, so you can see how it would map a 5 under IPP using 3 bits, or a 40 using DSCP using 6 bits. Since DSCP uses 6 bits, there are 64 possible classifications of traffic. QoS marking happens at trust boundaries, and marking should happen as close to the source as possible. Endpoints like voice over IP phones, wireless access points, and video conferencing gateways have the ability to mark QoS packets, as indicated in number 1. Traffic can also be marked using layer 2 switches, as in number 2, or at layer 3 using layer 3 switches and routers. As packets travel across the network, the remarking of the traffic can be necessary. The remarking of class of service values, or IP precedent values, or DSCP values. The main mechanism of congestion avoidance in QoS on Cisco routers and switches is weighted random early detection, or WRED. With weighted random early detection, a percentage of the packets are dropped once we've gone over in a queue the minimum threshold. If the queue has gone over the maximum threshold, then packets are automatically dropped. In this image, you can see the difference between traffic policing and traffic shaping. In traffic policing, when the traffic rate reaches the configured maximum rate, excess traffic is dropped. The result is an output rate that appears as a sawtooth with crests and troughs, as shown in the graph at the top. With traffic shaping, excess packets are retained in a queue and then rescheduled for later transmission over increments of time. The result of traffic shaping is a smoothed packet output rate as shown in the bottom graph.